Hi all. In this video, we are going to learn about a machine learning method known as logistic regression. So although its name carries the word regression, but actually it is an algorithm for classification. So one can say that this is one of the simplest algorithms for classification. So I would not call it the simplest because we have seen knife based algorithm in another video, which is certainly the simplest algorithm, but logistic regression also is quite simple to apply. So before that, what is a classification problem? So classification basically means that if you have some set of data, you want to group them in to different categories. So for example, you may have a problem where you want to classify your emails between spam and normal, which is what we saw earlier in the knife based algorithm video. Or let's say you have some kind of a tissue and you want to find out whether it is malignant versus healthy tissue. Or for example, if you have, let's say, some news which you are reading in a newspaper and you want to find out whether the news is fake or it is real. Or for example, you have an image that you see on Facebook or Instagram and you want to find out whether it is that of a human or an animal. Now for a human to do this classification is quite easy. Can a computer algorithm also be trained to do this classification? So these are some examples of binary classification problems. Binary because we have two categories over here. So we are going to see how you can use logistic regression to solve a binary classification problem. You could also have a multi-classification problem. For example, in this spam versus normal email, you may also want to classify this normal further into important and not important categories. So then you would have had three categories, and then your job is to figure out that which of these three categories your email lies in. So that is a problem of multi-class classification, which we are going to see in the next video. So in this video, for the sake of simplicity, we are going to focus on what is called binary classification. So now let's see how to solve this using logistic regression. So now obviously if you want to apply any machine learning method to solve a problem, you have to convert that problem in numerical terms, because a computer only understands numbers. So whatever words we are using over here, whatever categories we are using over here, we need to represent that using numbers. And for binary classification, what we do is that we use 0 and 1. So now what we have is a problem of binary classification where we have an output yi which can be 0 or 1. So what is this subscript I? This subscript I refers to the ith input. So you have multiple inputs which are coming in. You have, like, for example, multiple emails which you are receiving. So each I would correspond to each email. Or if you are doing fake news versus real news classification, each I would correspond to a piece of news article, and that can take two values, 0 and 1, because we are talking of binary classification. So for example, your 0 can represent spam and 1 can represent normal email. Your 0 can represent fake news and 1 can represent real news, and so on. So now what does this y depends on? Y depends on your inputs, which are xi. So you have some inputs xi, and that gives you your output yi. So now our job in logistic regression, which is a algorithm of supervised machine learning, is that for a given set of inputs xi, we want to predict the value for yi. So these xi's in general are vector quantities because each email, for example, has multiple features. You can, for example, have the number of words in the email or the number of times a particular word occurs. For example, if an email has a word money or lottery many times, then it is likely to be a spam email. So, or for example, the length of the email. So there could be many such features which could constitute each input data point. So that's why each input is a vector. Now in supervised learning, your output yi could also be a vector, as it is for the case of multi-class classification, which we will see in the next video. But in this problem of binary classification, your yi is just a scalar. So for now, yi is a scalar which can take values either 0 or 1, and your xi can be a vector of arbitrary length. Now what is our job? Our job is to predict yi given a certain input value xi. Now obviously no machine learning algorithm is perfect, and the reason is that the data on which it is trained is not perfect. If the data was perfect, your ML algorithm would also be likely to lead to perfect outcomes. But because data is noisy, so your learning is also imperfect. So what do we do instead is that instead of exactly predicting which output is corresponding to a given input, what we do is that we predict the probability of various outputs. So our job in logistic regression is to predict the probability of yi equal to 1 given a input vector. So what we want to predict is the probability of yi given xi and the parameter values theta. So theta are the model parameter values. And the job of the machine learning algorithm is to learn these parameter values which lead to maximum classification accuracy. So this probability we are going to denote by the function h. So this is our h given xi and theta. And this in some sense is your yi tilde. So this yi tilde is the predicted output for a given input data point and learned model parameter values. So now obviously, since our probability values can only be between 0 and 1, so this hi should also be between 0 to 1, and we will choose a particular function in logistic regression which will ensure that this hi is always between 0 and 1. So before getting into the actual mathematical formulation of logistic regression, let's try to visually understand what logistic regression is trying to do. So now let's say we are solving the binary classification problem, and now our input is just a scalar for simplicity. So it's a vector with only one element. What we can do is that we can plot our input and output. So let's say this is our xi axis and this is our yi axis. Now since it's a binary classification problem, our yi can take only two values, so it can either be 0 or it can be 1. So let's say this represents the value 0 and this represents the value 1. And let's say our for xi's over here yi is 0, and for xi's beyond a certain limit your yi is over here. Now this data is given to you and your job is to now find out that for a new value of xi, which may be, let's say, over here, how do you predict which class it belongs to, whether it is 0 class or whether it is class 1. So now here what you can do in the simplest possible case is to try to find a vertical line which does a perfect separation between these points. So let's say I may want to find out a single straight line, something like this, which does a separation between the two. So on this side, our yi tilde should be equal to 1, and on this side, our yi tilde should be equal to 0. So now the thing is that this is a perfect classification problem because we have a clear boundary and all the points with yi equal to 1 are on the right side and all the points with yi equal to 0 are in the left side. But this seldom happens in real life. So in real life, what we have is that there will be a few points which will lie on the other side, and there will again be a few points which will again lie on the wrong side of your classification boundary. So now, instead of exactly predicting the outcome, whether it is 0 or 1, you have to introduce a kind of probability. So you have to now estimate what is the probability that my point belongs to class 1 or to class 0. So what do we have? We have two things over here. Firstly, we have this line which is called the decision boundary, and then you need a function h of xi comma theta that gives you the probability of a given output for a given set of input data points and your parameters theta. And as the distance from this decision boundary increases on the right side, your h should slowly become equal to 1. And as the distance from this decision boundary increases on the left side, your h should slowly become 0. And usually when we do these things, we choose continuous functions because that helps in implementing gradient descent well. So now essentially your function has to be something that is 0 over here because you're far away from the boundary on the left side. It should slowly increase. As you cross the boundary, it should cross 0.5, and as you go further, it should become close to 1. So essentially you need a graph which looks something like this. So it starts from 0, remains close to 0, increases slowly, and then as you further increase, it becomes almost equal to 1. So this is your function h of xi and your function theta, and this method is called logistic regression because this function h is the logit function. So we will soon see its functional form, but I am now just telling you its name. So now you can do the same thing in two dimensions also. So let's say now you have two parameters. So instead of one parameter, your binary classification problem now has two parameters. So let's say they are xi1 and xi2. and you have some points, let's say over here, and you have points belonging to another category, let's say over here. So what is the job of logistic regression is to find a straight line which can classify our categories. So in this case, this is our decision boundary. And as the distance from this boundary grows on this side, the probability of h being 1 should be increasing. So as you go farther and farther away from the line on this side, your h should become closer and closer to 1. And as you go towards this side, farther and farther, your h should become close to 0. So now h will depend on x1, xi1 and xi2 and the parameter values. So this is the basic idea of logistic regression, and here it is important to remember that in logistic regression we always have a linear decision boundary. So this is one limitation of logistic regression also, that in other methods like SVM, support vector machines, or artificial neural networks, you can have nonlinear decision boundaries also. But in the case of logistic regression, you only have a linear decision boundary. However, like the case of linear regression, here you can have a kind of nonlinearity because each of these input parameter values or input feature values could be nonlinear functions of other features. So for example, this xi2 could be a square or a cube of xi1. So in such situations, you can have an effective nonlinear boundary in logistic regression also, but once you have transformed your variables into your input vector which goes into logistic regression, you have a linear boundary in that particular transformed space. So now basically what we do is that we have some input parameters and we have some model parameters that we want to learn, which we denote by theta. What we say is that if our theta naught plus theta transpose xi is greater than 0, then we must have our function h, which is a function of xi and theta, to be greater than 0.5. And if our theta 0 plus theta transpose xi is less than 0, then we must have h of xi comma theta to be less than 0.5. So now here just it's bad notation, but remember that this theta over here includes our theta naught also. Okay, so that is just, I am not writing it here, but you should remember that this theta over here includes this vector theta as well as this theta naught also. So now we need two things to make further progress. First of all, we need an expression for h, which is our hypothesis for logistic regression, and then we also need a cost function or loss function which we will minimize. So now how do we choose a hypothesis function for logistic regression? So as I told you that for logistic regression we choose what is called the logit function. So now what is this logit function? It is also called the sigmoid. So the logit function is given by h of xi comma theta. Let me also write theta 0 over here for the sake of clarity. This is given by 1 by 1 plus e power minus theta 0 plus theta transpose xi. So if you remember, the condition we had is that if this quantity is positive, then our h must be greater than 0.5, which you can test. So if this is positive, then this is minus, so this quantity is less than 1. And if this quantity is less than 1, then this ratio will be more than 0.5. And then if this quantity is negative, then negative into negative will be positive, so then this exponential will be more than 1, in which case this ratio will become less than 0.5. So we can see that this hypothesis function satisfies our condition, and also h is always between 0 and 1, because this ratio can never become negative and it can never become larger than 1, because this exponential will always be a positive quantity. So we can see that this choice of the logit function satisfies our two conditions for the choice of the hypothesis function. There is also another reason for choosing this hypothesis function, which is that you can rewrite this in a slightly different way. So I am not going to do all the steps, but if you do some simple manipulation, what you will find is that hi divided by 1 minus hi. So this is called the odds. So in hi represents probability and this represents the odds. So sometimes we say, what are the odds of the Indian cricket team winning in Australia? So this is the mathematical definition of odds. So this quantity is what we denote by hi, and this is the probability. And if you take a log of this quantity, what you will find is that this is equal to theta 0 plus theta transpose xi, which is our linear transformation of the input data point xi. So the log odds of our hypothesis function is a linear function. So this is another motivation for choosing this logit function or the sigmoid. So now we have come quite far. So we have defined our problem. We have chosen our logit function, which is our hypothesis. And now what we need is a cost function, because we want to learn the parameters theta which maximize our classification accuracy. So now one option is to use the least squares error cost function, which we had used in the case of linear regression. So if we do that, what we will have is that, so let's say we want to use the least squares error loss function. So in that case, what we will have is that our cost function LSE, which is a function of the parameters theta as well as theta naught, that will be equal to 1 by n, where n is the total number of input data points, summation I is equal to 1 to capital N into yi, which is the known output, minus hi whole square. And this is what we would want to minimize. But the problem over here is that for logistic regression, the least squares error cost function is not convex. This is a serious problem, because if you remember the video on gradient descent, what happens is that if you do not have a convex function, so let's say this LSE looks something like this. So although this graph has a global minimum, which is here, but you may get stuck in the local minimum. And this is a problem with non-convex functions in machine learning. So when we go to artificial neural networks and other advanced algorithms, so there you do not have convexity. That is a problem. But if it is possible to have a convex optimization function or a convex loss function, you must always choose that. So in the case of logistic regression, the good news is that it is possible to have a convex optimization function for estimating our parameter values. And as it turns out, the choice that we make is the binary cross entropy loss function, which I had introduced to you in the video on maximum likelihood estimator. So what is that function? Let me remind you. So for binary classification problems, we generally choose the binary cross entropy function. So what is this binary cross entropy function? So this is given by, so our C, the cost function as a function of the parameter values, is equal to 1 by n summation I is equal to 1 to n minus yi log of hi minus 1 minus yi into log of 1 minus hi. So we had derived this in our video on maximum likelihood estimator. So in case you don't remember, please go back to that video and take a look. So now just to get some intuitive idea about how does this binary cross entropy function help us in minimizing our loss. So let us draw a simple plot. So on the x-axis is our hi for a given I, and the y-axis is equal to ci, which is the cost function for a particular I value. And now let's say that your yi is 0. So if yi is equal to 0, then your ci, which is that particular term, is equal to minus log of 1 minus hi, because when yi is 0, this term becomes 0 and what remains is this. And here if yi is 0, you just get 1. So what remains is minus log of 1 minus hi. Now we are ignoring this 1 by n over here because that is just a multiplication factor. So if your yi is 0, your ci looks like this. So now let's try to plot it. So let's say that this point on the x-axis is 0 and this point is 1. Now we know that our hi will never be larger than 1, so we can be in this range. So now when hi is 0, so when hi is 0, 1 minus 0 is 1 and log of 1 is 0. So now we are then starting from here, 0. As hi becomes equal to 1, so when hi is equal to 1, 1 minus 1 becomes close to 0. So this becomes closer to minus infinity. So negative of that becomes close to plus infinity. So as hi gets closer to 1, this ci increases to minus infinity. Now let's take yi equal to 1. So if yi is equal to 1, our ci is equal to minus log of hi. And why is that? Because when yi is 1, 1 minus 1 cancels out, so this goes to 0. And so here what we have is just minus log hi. So now when hi is equal to 1, this is equal to 0. So now we start from here. Hi is 1 and ci is 0. As hi decreases towards 0, obviously ci will start increasing till it goes to infinity. So now do you notice? So when yi is 1, we want hi to be close to 1, and if that happens, we want ci to be close to 0, because that is the objective of minimizing the cost function, meaning that when I am making the right prediction, my cost should be as low as possible. So when our hi is close to the value of yi, the ci has to be close to 0. And that happens in this case and that happens in this case also. So when yi is 0, the cost function is small when hi is close to 0. So that is the intuition behind the binary cross entropy function, and it is possible to show mathematically that this is indeed a convex optimization problem. So for the case of logistic regression, binary cross entropy function is convex. For artificial neural networks, it is not convex, but for logistic regression, it is convex. So this is convex for logistic regression. So now we have our hypothesis function which we have chosen to be the sigmoid, and we now also have our loss function or the cost function which we have chosen to be the binary cross entropy function, and now our objective is to estimate the model parameter values which are theta. So how do you do that? You do that by using gradient descent, which is the standard algorithm for all machine learning problems. So I hope this video has made clear the concept of logistic regression for you, and I strongly encourage you to actually implement it using Python code. The link of Python implementation is given in the description box. So please do take a look and thereby improve your understanding of logistic regression. In this video, we have covered the case of binary classification using logistic regression. In the next video, we will see how to do multi-class classification using the same methods of logistic regression. Till then, stay connected.